Okay, wonderful. Good morning, everyone. I welcome you back to my YouTube channel and presenting this wonderful tutorial is the mentor Hampeo Kliman. And then today we are going to be doing a very important physics session. We shall be solving physics questions. Then we see how best we can help each other. And of course, if you are new to the channel, consider subscribing, hitting the like button, and don't forget to share. Etsy Learning Academy, don't forget to register for personal lessons if you don't seem to understand what you are studying. The school is open. It's only 100 kwacha each course monthly, as you are able to see on the screen. Okay, so of course, if you want to inbox the mentor, it's just plus 26077664046, and I'll be able to register you for whatsoever course that you want to be registered in. And of course, we will be having our Elroy experience at Mulungushi University with Apostle Alex BC Mutale and Pastor Priscilla Mutale. And of course, you will need to be there. The venue is simply the Mount Pepos Hall at Mulungushi University, and it will be taking place on Friday, which happens to be 1st May 2026. What is the time? It is 18 hours up to 05 hours. Don't forget to come to the presence of God. Let's proceed. Look, we have very special questions. The first question is saying, in a circuit, a capacitor has a potential difference. Okay, so we have a capacitor with a potential difference of, okay, so we're having our PD. Our PD is simply V, our capacitor represented by the letter C, our charge represented by the big letter Q, right? But one thing that you must be able to know is that charge is simply the product of your capacitance multiplied by the change in potential difference. This is the formula that we use. Now the question is saying, in a circuit, a capacitor has the potential difference, change in V, then a capacitance C, and the charge Q. The potential difference is doubled. The capacitance dash. Now what happens in this formula when you double the potential difference? Let's say potential difference happens to be 2. You will discover that what is going to be affected is the charge. In that, when you double the PD, or when you double the potential difference, you are doubling the charge as well. So you increase the charge, you increase the potential difference. That is the concept behind. But you will notice that the capacitance is not being affected by the potential difference. Okay? Capacitance is only affecting the charge and not really the potential difference. So you expect it to just remain the same. Okay? You expect it to remain the same. Henceforth, our answer is going to be C. Okay? It won't change. We go to 2. To increase the capacitance of a parallel plate capacitor, you can, to increase the capacitance of a parallel plate capacitor, you can A, increase the distance between the plates, B, increase the areas of the plate, C, all of the above, D, none of the above. Okay, so I want you to look at this formula. Capacitance, okay, this was the first. Capacitance is given by the formula. You are going to have this constant, which we aren't interested in, this constant multiplying with the area over your distance. Okay, area over the distance. Now I want you to see how this one is affected. When you increase the area, what happens to the capacitance? The capacitance also increases. Okay? But when you increase the distance, and then you maintain the area, you discover that your capacitance will be reducing. So the only way you would increase capacitance is when you increase or you double the area. If you increase the area, at the same time, you reduce the distance. You increase the area, you reduce the distance, or you maintain the area, but you just reduce the distance. You discover that this value is going to be increasing. So to increase the capacitance of a parallel plate capacitor, you can just increase the area. Okay? That's the concept behind. 3. If a conductor has potential equal to 0 and there are no charges anywhere else outside, then if a conductor has a potential equal to 0, right? A conductor has got a potential which is equal to 0 and there are no charges anywhere else outside. Then, so remember, imagine you have an object and that object has got a potential difference equal to 0. Nothing really is ongoing. No net charges anywhere else, nothing. Okay? Then A, there must be charges on the surface or inside itself. B, there cannot be any charge in the body of the conductor. C, there must be charges only on the surface of the conductor. There must be charges inside. So, look, if you are the body and that body has got a potential difference equal to 0, the potential difference equal to 0 implies there is no electric conduction happening. It's neutral. Nothing is occurring, right? And there are no charges anywhere else outside, meaning there is no external influence either. So there's literally nothing occurring. So there cannot be any charge in the body of the conductor. It's not possible, right? It is not possible. Something that is neutral and then on the outside no external force acting on it, it can't be charged. Okay? Remember, charging is either conduction or induction. That's when the body is going to be charged. So there cannot be any charge in the body of the conductor, which is B. We go to question 4. Equipotential at a great distance from a collection of charges whose sum is not equal to 0 are, okay, so for this one, it is spherical. 5. Consider a uniform electric field in the z direction. The potential is constant. Okay, consider a uniform electric field in the z direction. The potential is constant. Okay, the potential is constant in A in all directions, B for any x for a given z, C for any y for a given z, D on the xy plane for a given z. Okay? So remember, you consider a uniform electric field in the z direction. Z direction implies, okay, so you have electric fields moving in this direction. You have some electric fields that are moving in, you can use the z concept, but at the same time you realize that this one, if you are considering this one as a magnitude vector, then of course you also need to find the electric fields of its components. So you discover that at the end of it all, for them to be able to cancel and arrive at some point where the net electric field is 0, there must be an electric field which is going to be moving in the which is going to be moving in the y-axis and also in the x. Okay? So your answer is going to be D. Okay, let's go to 6. Question 6. A positively charged particle is released from rest in a uniform electric field. The electric potential energy of the charge, okay, a positively charged particle is released from rest in a uniform electric field. The electric potential energy of the charge is A, remains constant because the electric field is constant, increases because charges moves along the electric field, decreases Okay, let's do this. We've got a positively charged particle. This particle is positively charged, is released from a rest in an uniform electric field. So let's say we have another particle here which is producing these electric fields. So if this guy is producing an electric field, right, in this direction, right, the moment the electric field gets in contact with what is already here, you expect uniformity to take place. These ones won't be able to cross just like this, no? They'll have to join uniformly with the electric fields which are being produced. Now, because of that uniformity, those that are being produced at a very strong rate, discharge, they might be able to penetrate, but with the slowness. Why? Because there is an interaction with the electric fields that have already been produced. Okay, it's kind of more like you're producing an electric field in this direction, then you have another one which is coming like that. Okay, this one A, you've got B. A must be strong enough to penetrate. If not, it will be able to join together with the fields that B is producing. That is uniformity. But if A was to cross, then eventually it will cross, yes, but with a small energy. It has to decrease. Okay? So, of course, my answer is going to be decreases because charge moves along the electric fields. Okay? That is going to be my answer. Okay? 7. A charged particle is moving in a uniform electric field. For the motion of the particle due to the field, which quantity has a constant? Non-zero. Which quantity has a constant? Non-zero. Okay, so they want us to find a quantity which is going to have a constant non-zero. A charged particle is moving in a uniform electric field. For the motion of the particle due to the field, which quantity has a constant non-zero? Okay, let's do this. We know that the electric field is equal to the force over the charge. So if we do this, we discover that your force is equal to the electric field depending on the charge. Now remember, this is Coulomb's force, and from Newton's second law of motion, force is directly proportional to the acceleration and indirectly proportional to the mass, right? Force is directly proportional to acceleration and then indirectly proportional to the mass. So you discover that you're going to have force. Force is directly proportional to the mass, right? And acceleration should be like that, but acceleration should be inversely proportional to the mass. Okay? In other words, what I'm trying to, let me explain from the formula. You have your force is equal to ma, right? Okay, when I explain to the formula, you understand what I'm trying to mean. If you discover that when you increase the mass, you are increasing the force. When you increase the mass, you maintain acceleration, force will still increase. When you increase acceleration, you maintain mass, it will still increase. But check out this. If I was to make acceleration the subject, then I make force constant, you discover that if I increase the mass, what is reducing is the acceleration. So for every object, the acceleration is directly proportional to the force and indirectly inversely proportional to the mass. And that's the correct Newton's second law of motion. Now, if we bring Newton's second law of motion in Coulomb's formula, where we say ma is equal to electric field multiplied by the charge, right? Then we make mass constant. You discover that acceleration is going to be affecting the electric field at some point charge. So this is the only factor which is going to be, this is the only quantity which will remain constant, okay, in relation to the electric field and the charge only. Okay, that's the only. So displacement can't fall in this relationship. Velocity, there is no way velocity can fall in this relationship. Rate of change of acceleration should be the velocity itself. Okay, so basically they just want you to bring in Newton's second law of motion, then you relate the acceleration to the what's this, the electric field and the charge. That's what it means. Question 8, let me explain. An ore droplet has a charge, negative Q, and is situated between horizontal metal plates, as shown in the diagram. The separation of the plates is D. We've got a plate on top, like that. Another plate downward. They are saying this one is positive V, this one is negative V, then this one is D. Then you've got a droplet, of course, which is negative. They are saying the upper plate is at potential positive V, and the lower plate is at potential negative V. For this to occur, what is the weight of the droplet? I want you to look at this. So the concept that you are going to use is for the electric field. Now, electric field, there's a formula. Electric field is equal to where you are going to have your voltage over some distance. Okay, this formula is something that you derive from the formula that we have here. Okay, you've got your field is equal to your potential difference over your D, which is the distance, some distance which is here, right? I want you to look at this. What is the change in V? The change in V, we've got positive V minus, then we've got negative V, all over by, then you've got some distance. At the end of it all, your EF is going to be V plus V over some D. Then you get this formula, right? You get this formula. You now, let me wrap the board. Let's try to get that formula and relate it to the force. Remember that the electric field was equal to the force over the charge. If you cross multiply, your force is going to equal to the electric field, then the charge. Now the electric field, we've already found it to be here. So now let's see if I put it in there, what is going to happen. So this is going to be 2V, then multiplied by some Q over the distance. Now remember, this is force, but they are asking us saying, let me see, what is the weight of the droplet? Remember that force is measured in newtons, weight is also force, just going downward, measured in newtons. So you can replace where there is force, you just put your weight, and then you're going to get your 2VQ over D. Let's see if we have anything like that. Okay, that one is going to be B. Okay, that's how I've solved it. That's how you should be able to solve these questions. Okay, let's now try to see if we can use anything similar. Question 9. Okay, so we have a question that said 2 large metal plates are separated. Okay, let's use the same concept. We've got this metal plate and another metal plate. They are being separated by a distance of 4 millimeters, which is just like 0.004 meters. Okay, if not really, okay, 0.04. Okay, divide by 4, divide by what? Okay, 0.004 meters. just divide by 1000. So now this is what is going to happen, right? That is the distance. Then we have been told that the lower plate is negative 80 volts. The upper plate, which potential should be applied to the upper plate? We don't know. Then what have we been given? We have been given the electric field to be 60,000. We use the same concept. Electric field is equal to, you get the one which is on top minus, because it's a difference, it's a potential difference, minus, then you get the one which is on the lower plate over the same distance, which is 0.004. Then you can put your 60,000, then this is going to be x plus 80 over 0.004. You cross multiply, let's see what we are going to have. So we've got 60,000, 1, 2, 3, multiplied by 0.004. So I'm getting like a 240 this side is equal to x plus 80. Then we subtract 240 minus 80, 160. So our x is 160. Okay, 160 plus. So this is going to be like, this is okay, 160 plus. This should be a positive, because the one on top is the positive. So the one on top is basically a positive, so it should also be positive. It should be a positive answer, right? If we are calculating the one which is on the lower plate, of course it could have been negative. We go to question 10. We see how best we can answer. We use some concepts. We see if we use the concepts, if we are going to get something sensible. What do we have in the question? The question is simply saying a particle has a charge. So the charge of the particle is simply 2.0 multiplied by 10 to the power 6 coulomb. By the way, if you've got microcoulomb, if you've got, let's say, a charge of 2.0 microcoulomb, just multiply it by 10 to the power negative 6 and you take it in coulomb. They're saying, and is in a vertical uniform electric field, an electric force. So you've got the electric force, which is the Coulomb's force of 1.0 multiplied by 10 to the power negative 2. It's acting upward. What is the electric field? They want us to calculate the electric field. We know that the electric field is simply the force over the charge. So in this case, our force is 1.0 multiplied by 10 to the power negative 2. Then divide by our charge, which is 2.0 multiplied by 10 to the power negative 6. Let's see if we're going to get anything beautiful after doing this. So 1.0 multiplied by 10 to the power negative 2, divide by, okay, let me divide by 2.0 multiplied by 10 to the power negative 6. Let's see. Electric field is giving like 5,000, that's in millivolts. Okay, so it's giving me 5.0. So of course it should be millivolts. Now let's say a particle has a charge of this and is in a vertical uniform electric field, and the electric force of this acts upwards on the particle. What is the electric field strength? So you must follow the line of the electric force. Where the electric force is going, that's why it should also go. Okay, so let's see. They're saying 5 upwards. Okay, I'll go with 5 upwards. Okay, so basically That is how you go about these questions. Okay. By the way, it's supposed to be watts per meter because, okay, this is what I was rushing to. This is what I really wanted to solve. Basically, that is going to be so involving. Make sure you attend the Elroy Experience Mulungushi University with Apostle Alex B.C. Mutale from Upper Room Nation. He's coming to preach to win souls to Christ and do many things based on what God has put in his heart. Apostle Alex B.C. Mutale will be there Friday, exactly 18 hours to 05 hours. It's gonna be a mighty overnight with a mighty God. So make sure you attend, you pray. Don't be busy for God. 1st of May, which happens to be Friday. The mentor Hampel Kliman is also going to be there. And of course, if you've loved how we've solved the questions, you are enjoying, make sure you register for personal lessons with your favorite, the mentor Hampel Kliman. Okay, let's try to simplify section B. Section B, we are going to do it slowly but surely. I'm going to explain things that you really need to put in your heart. Okay. We have a question here where they are saying charge Q1 is equal to 7. Okay, so we've got a charge Q1 is equal to 7.0 microcoulomb, then Q2 is equal to negative 5.0 microcoulomb, and then we have been taught that it is actually in the y-axis, so it's located at 0.03 meters. This one, where is it located? This one is located at 0.0. From the origin, find the magnitude and direction of the electric field at point P. So what we want to find is point P. This question has just been changed, but I'll show you just how to go about it. So look, the origin is where point Q1 is. So this is where Q1 is. Then we have been told that in the y-axis, this is where your Q2 is. And then the distance between Q1 and Q2 is 0.3 meters. Then point P, find the magnitude and direction at point P, which has coordinates 0.4, 0. So point P is in the x-axis. This is the x-axis. So point P is at 0.4, 0. So it's in the x-axis. So this is where point P is. And then it's going to be 0.4. 0.4 meters. What else is significant from the information? Okay, so this is going to be our diagram. Now they are saying we find the magnitude and direction of the electric field at point P. The way to answer this question, you are going to find the magnitude because this guy here is positive, right? This guy here is negative. This one is neutral, we don't know. So there's going to be some repulsion force due in this direction and also a repulsion due in this direction because you don't know whether it is charged or uncharged. But all in all, this is in the x. So you'll find the electric field due to Q1 at point P. So we start with this line here. So your electric field is equal to some K. Then we find our Q1 due to QP, right? Q1 due to QP. Okay, so you can even state, say this is going to be, let me just put it as 1, let me put this one as 2, let me put this one as 3. So it's going to be 1, 3 all over by r to the power 2. This is 8.99 multiplied by 10 to the power 9. In absolute values, this is going to be, okay, this is 7.0 multiplied by 10, because you are taking it in columns, yeah, multiplying by -6, all over by the distance is 0.4. So let's multiply that. 8.99 multiplied by 10 to the power 9. 7.0 multiplied by 10 to the power -6. Divide by -4 to the power 2. 1, 2, 3, 4, 5. So we're getting something like your electric field is going to be 3.93 multiplied by 10 to the power 5 Newton Coulomb. Now, remember, the path is in the x. And because the path is in the x, there is no other component that we can find. There is only one component, and that component is in the x. So we have found due to that one. Now, for Q2, due to Q3, this line here, this is where I want us to pay extra attention. HC, I taught you, you are supposed to extend some lines so that you are able to see properly what you are doing. Then you also extend a line, okay, like that, so that you make a box. Then it will be able to show you properly what you are doing. So now you have this, and then you're going to have that. So you need to find this angle here. Find that angle there. Then this becomes your hypotenuse. Okay, then this becomes your adjacent. This becomes your opposite. So now let's try to find the field due to this line here. So electric field due to Q3 is going to equal to some K, then of course Q2 over R to the power 2. So this is just going to be 8.99 multiplied by 10 to the power 9. In absolute values, you won't put the negative, just put your 5, because you already know it's negative because it's moving in this direction. It's going downward like that. Okay, so this is 5 multiplied by 10 to the power -6 all over by, this is going to be r to the power 2. R to the power 2. Now this distance, what is this distance? We can find it, the hypotenuse. So hypotenuse is simply some x is equal to, then we can say 0.3 plus 0.4 to the power 2. Then this is going to be x to the power 2. Okay, let's try to calculate that. So this is 0.3. Okay, 0.3 power 2 plus 0.4 power 2. Then we square root, we are going to get 0.5. So this is going to be 0.25. X is going to equal, find the square root of that. Come on. Find the square root of that. Okay, let's do this. Because we've already introduced the square root, so no need. Okay, I'm getting 0.5. So this distance here is 0.5. That distance there is 0.5. Now let's try to calculate the field. So we put our 0.5 here. I want you to see. You use the same concept I'm using for any question. even if they change it in whichever way, you'll still be able to get something sensible. Just follow the steps properly. Okay. Okay, so 8.99 multiplied by 10 to the power 9. Then what we have 5.5 multiplied by 10 to the power negative 6. Divide by 0.5 to the power 2. So we are getting something like 1.79 multiplied by 10 to the power 5. Okay? 1.79 multiplied by 10 to the power 5. Newton Coulomb. Now, this one that we have is just the electric field general. Now, we are supposed to find the electric field because, look, it's moving at an angle, right? It's moving at an angle theta. So, let's try to see if at all we are going to get anything sensible. So, let's try to find this theta here. Okay, let's try to find our theta there. We see what we are going to get. So, okay, we have calculated for the electric field due to Q2 to P3. Now we need to compute it in two components because there are two components. There is this component, there is this component, right? X and Y component. Now, let's try to calculate some angle, we see, because this one is your 90 degrees. So your 90 degrees is your adjacent. This is your opposite if we are using this angle here. Okay, if we are using that angle, let me show you. If we are going to calculate this angle, then we need to calculate this one first. Okay, let's calculate that one. So, and see if we're going to get anything serious. So how do you calculate the angle? To calculate this angle here, we are using adjacent and hypotenuse. So that is cosine theta. Okay, cosine theta is equal to adjacent over hypotenuse. Theta is equal to cosine inverse of what is the adjacent. Adjacent in this case, I've turned the triangle. I want to calculate this angle here. So it's going to be 0.3 over 0.5. Let's see what we get. Shift of cosine 0.3 divided by 0.5. 53. So theta is going to be 53.13. Now let's see. Because this is the theta for this one, so this is going to be 53.13. Now, for me to find the theta in blue, I need to say 90. Okay, 90. Okay. Okay, for the sake of learning, which trying to simplify everything as simplified as possible. So the entire of this thing here is 90. Then we have the theta here. We want to calculate this one. So to calculate that one, we are going to say 53.13 plus the theta we want to find. Collectively, everything is equal to 90. So our theta is going to 90 minus 53.13. Let's see what theta is going to be. It's going to equal to, okay, so it's going to equal to 36.80 degrees. So now we have this one. We have the theta in blue. So if we're using theta in blue, to calculate components, this is going to be the adjacent and this is going to be the hypotenuse. So we can now do the needful. Okay, so we had one, let's say electric field in the x is going to equal to, so what do we have? 1.79 multiplied by 10 to the power 5 Newton per Coulomb. But now let's try to find in the x, so it's going to be multiplied by cosine 36.86. Let's see if we're going to get something. So we have 1.79 multiplied by 10 to the power 5, then cosine 36 point. Let me make an emphasis. Look, this is the angle we are using here. If this is the angle, you have this pointer, this becomes your hypotenuse, this becomes your adjacent. This is the adjacent. So this one, for you to find this line, you are using cos. For you to find this line, you are using sine. It's not always that you're supposed to use cosine in the x, sine in the y. Know where the adjacent is. What the adjacent is for a triangle, that's why you use cosine. Where your sine is for a triangle, that's why you use sine. Okay? So let's see what is going to work. 38 point, this is going to be like this. Okay, so we're going to find like 1, 2, 3, 4, 5. Okay, so we're getting something like 1.43 multiplied by 10 to the power 5. Okay, like that. This is in the x. Now you realize that because this guy is supposed to be negative in the x, so you expect this one to be negative, right? But for y, it's going to be positive. Okay, for y you expect it to be positive. Now let's see electric field during the y. So I'm still getting the same thing. But this one will be sine 36. How about if we use sine? It was be long we solved such very interesting questions. Then this one is going to 36.86. Okay, this one is simply 1.073 multiplied by 10 to the power, let me see, 1, 2, 3, 4, 5. 5 even as well. Now in the x, remember we had found this one, so we can also get it. We now find everything resultant in the x, so 3.93. Okay, so we are going to say resultant in the x is going to equal to 3.93 multiplied by 10 to the power 5, then minus. We're supposed to add everything in the x, but since this one was a minus, so I have taken time to explain this so that you understand. What are we going to have? 3.93 multiplied by 10 to the power 5 minus 1.43 multiplied by 10 to the power 5. We're getting like 2.5, so 1, 2, 3, 4, 5. This is going to be like 2.5 multiplied by 10 to the power 5 Newton per Coulomb. So this is what we are going to use as the final. How about resultant in the y? Remember, in the y we had a 0 for the first one. Then for the second one, what did we have in the y? We had this one. So we are going to add it to this one. So 0 plus this, we find everything in the y. You discover that you're going to get 0.73 multiplied by 10 to the power 5 Newton per coulomb. We can now find the resultant final. Okay, let's see what we are going to get. So this answer power 2 plus 1.07 multiplied by 10 to the power 5, then power 2. Then we find the square root. Okay, so when I get the square root, I'm getting something like the resultant electric field 1, 2, 3, 4, 5. 2.7 multiplied by 10 to the power. It's 2.72. I'm getting 2.72 multiplied by 10 to the power 5 Newton per coulomb. This is the resultant. Now we can find the direction, which happens to be theta is equal to some tan inverse of whatever was in the y. So in the y, what did we have? We had 1.073 multiplied by 10 to the power 5. All over by in the x, we had 2.5 multiplied by 10 to the power 5. Let's see. So it's a tan inverse of shift tan. Then we have 1.073 multiplied by 10 to the power 5 all over by 2.5 multiplied by 10 to the power 5. Follow me well. Okay. So 1.073 multiplied by 10 to the power 5. Okay. Then all over by 2.5 multiplied by 10 to the power 5. Okay. So to me, theta is giving me something like 89.9 degrees. Okay, that's what I'm getting. That's what I am getting for this particular question. Okay, you can also try to put it in, let's see. Okay, let me do this. 1.07. So whenever you are putting in standard form, make sure you try as many times, because this could be your exam and then you want to be sure. Okay, you want to be sure of what you're doing. So you can say shift tan zeros of answer all over by 2.5, sorry, 25. Okay, this is going to be 25 and 5 zeros. 1, 2, 3, 2, 3, 4, 5. Why is it giving me something else? Something different. Done. Right, 0.73 multiplied by 10 to the power 5 divided by 2.5 multiplied by 10 to the power 5. Okay, so you try around on the angle. Okay, so oftentimes, usually you're supposed to expand this, just put it in its normal form so that you are able to get your answer and you find your resultant in the y, your resultant in the x, but it should give you an angle somewhere. Let's see how the question proceeds. It says, find the force on a charge 2.0 multiplied. Okay, so we've been given a force. They're saying we find the force when they, let's see, when they find the force on a charge. Oh, we've been given a charge of 2.0 multiplied by 10 to the power -6 coulomb. And we have the electric field to be 2.5. Sorry, the net electric field. Okay, I better need some water. I'm starting to get tired. Okay, we want to find the electric force, but you know that the electric force is simply the electric field multiplied by the charge. This we already know. Please make sure you assess the angle, but not in standard form. Okay, 2.72 multiplied by 10 to the power 5 multiplied by 2.0 multiplied by 10 to the power -6. Two 2 multiplied by 10 to the power 5, then 2.0 multiplied by 10 to the power -6. Okay, we are getting the force of 0.544 newtons. Okay, basically this is what we are able to get. Okay, for everything when you calculate that. Okay, so quite a long journey. We now solve C question. I'm going to skip B because it's not really important at this moment. Okay. 3 charges lie along the x-axis. The positive charge, that is question 3. Let's now do this. Wrap this. Look at this HC. I'll be able to solve C so that you understand. The manner in which I'm going to solve it, make sure you really pay attention. 3 charges lie along the x-axis. The positive charge Q1 is at x is equal to 1.5 meters. And the positive charge Q2 is at the origin. So look at this. Q2 is at the origin. Then Q1 is at some point where the entire distance is 1.5 meters. Please follow the concept, follow what I'm going to do. Where must a point charge Q3 be placed so that the resultant electric force is 0? I taught this at HC Learning Academy, but I'll be able to. The question has been changed, so you'll see the concept to use. So you put a point charge in the middle, then from Q2 to the point charge, you say X, then from from the point Q3 to the point charge, you subtract that distance minus X, right? Now you use Coulomb's force. Coulomb's force, okay, let's see, which is what? Okay. Okay, Coulomb's force is equal to some K, okay, some K, then this is going to be Q2 multiplied by Q3 over some distance r to the power 2. Then the other Coulomb's force is going to be K, then it's going to be Q1, Q3 over some r to the power 2. So this is going to be Coulombs due to 0.1, this distance Coulombs due to 0.2. Then you're supposed to equate Coulombs due to 0.1 equal to Coulombs due to 0.2. So if you equate them, you discover you're going to have something like Coulomb's force Q2, Q3 over r to the power 2 is equal to Coulomb's force Q1, Q3 over r to the power 2. You can cancel out this and cancel out the K. Cancel out the 3, cancel out this. At the end of it all, you're going to remain with Q2 over r to the power 2 is equal to Q3 over r to the power 2. This is the 2 we shall use. Now let's use it. What is Q2? HC, look at this. Do not change the what you have been given the units. Don't put them in columns. Just take them the way they are for this particular type of questions. I taught this at HC. Please make sure you register for personal lessons. That's the importance of having a mentor who is present for you in your life. Let's use that. What is Q2? Q2, we have been told that it is 10 coulombs. So I'm going to put my 10. I haven't changed the units. I've just gone directly. What is X? What is R2? Okay. So the distance here was X. So the distance was X. So I'm going to put my X but to the power 2. Put your X there. How about Q1? Q1 we have been told that it was 15 coulomb. So I will get my 15 directly. Then what is the distance of Q1? It was 1.5 minus X to the power 2. Let's try to expand that. 1.5 minus X, 1.5 multiplied by, minus X. Okay, minus X. So minus X like that. 1.5 multiplied by 1.5. So 1.5 multiplied by 1.5 is 2.25. Then 1.5 multiplied by that is going to be minus 1.5x. Then minus 1.5x. Then plus x to the power 2. So together, we cross multiply. We are going to have 10. Open the bracket. Then this is going to be like x to the power 2 minus this is going to be 3. Then this is going to be plus 2.25 equal to, then this is going to be 15x to the power 2 when you cross multiply. Now this is going to be 10x to the power 2 minus 30x plus this is going to be like 22.5 equal to 15x. So let's now make a quadratic equation. So if we push everything on the other side, we're going to have plus 30x because it will be positive minus 22.5 and equal to 0. So our A Okay, let's see what we have. Okay. Okay, that is basically what we are going to have at the end of it all. Now, we will need to proceed. So now, how do you go about solving such a question now, whereby you've now been given whatever you have been given? So we can now proceed. We see how best we are going to have our answers. Okay, so our A is going to be something like 15. Our B okay, let me just breathe in. Okay. Okay, let me just have maybe some water. Beautiful. We now proceed. It's very important to breathe in, to breathe out, to increase oxygen concentration in my brain cells, hence enabling them to expand information at a very, very strong speed beyond light. Okay, so we now take this guy this side, so it's going to be like 15 x to the power 2 minus 10 x to the power 2 plus 30x minus 22.5. So this is going to be like 5 x to the power 2 plus 30x minus c, okay, equal to 0. Now let's try to do some beautiful magic. We see. The question is, do you use the same concept over and over and over and over again? Yes, you do. Yes, you do. So now, some distance x is equal to minus b, positive or minus the square root of b to the power 2 minus 4ax over 2a. X is going to equal to, so minus 30 plus or minus, what is b? B is 30, a is 5, c is minus 22.5, all over by 2, then 5. Okay, let's try to see if we're going to get any, sorry, it's supposed to be power 2. So let's see, 30 to the power 2 plus 4. I know it will be a plus in there because of the 5. Because of the negative 225. Okay, so we are getting 1350, then we find the square root of 1350. We are getting minus 30, positive or minus 36.74 over 10. Now you asked me, which figure do you get whenever you're finding the final answer? Get the one which is positive. So you can only get a positive when you are adding. So forget the minuses. Okay, so the only answer that, the only positive outcome is when you have negative 30 plus 36.7. Okay, minus 30. That's the only way you'd get a positive. That's what I thought. And our final answer is 0.67 meters. So, for you to be able to get for you to be able to get a resultant electric force equal to 0, you must put a negative charge, Q3, at some point 0.67 meters, and that becomes your final answer. Well, thank you so much for traveling with me in physics. If you found this video interesting and helpful, don't forget to subscribe, hit the like button, and don't forget to share to others. Above all, don't you forget to register for personal lessons, especially if you have issues in your physics. The mentor Humble Kliman from HC Learning Academy, and of course Elroy night Friday exactly Mulungushi University with Apostle Alex BC Mutale. Don't you forget. Thank you so much.